let's look at these equations and we're going to turn them into exponential form. This is something you'll see on Derivita. So if I have log base 2 of 32 equals question mark, let's turn that into an exponential equation. So I know that my 2 value is the number that we're raising a power to in order to equal our 32. So I have to raise 2, I know, to the power of 5 in order to get 32. But if it just wants you to write it in exponential form, you're just going to write 2 to the power of 5 equals 32.
All right, let's do that same process here with b. So we know log base 2 of a half equals something. So 2 is my base. I know logs tell me what exponent do I need to raise the base to in order to get that inside. So 2 raised to something gives me my inside. So 2 raised to something gives me that 1/2. If I ever have a fraction, I know I'm dealing with negatives with my exponent. So I know that 2 to the negative 1 is the same as 1 over 2 to the first power. Remember that negative just turns into a positive in its fraction form, or the exponent becomes a positive in the fraction form. That's an exponent property. And so I know that 1 divided by 2 to the first power is the same as 1/2. And so I know that this question mark has to be -1. So I can say log base 2 of a half equals -1. So the answer would be -1.
Okay, let's look at C. It says log base 2 of 4 equals what? So same thing we did here. Our base is going to be raised to, we're not sure what power, in order to equal 4. Well, if I look at this, I know that 2 to the second power gives me 4. So I know that my answer here is 2.
Here we have log base 2 of 0 equals something. So I know that 2 is my base, and it's going to be raised to whatever the question mark is, and that equals 0. Well, 2 raised to anything can never give me 0. Remember when we were graphing our exponential graphs, we always have that asymptote right at y equals 0, because I can't take a number and raise it to some power to get nothing, because I already started with a number. And so I take a number and I raise it to a negative number or a positive number or even 0, I won't ever get 0 because I have that asymptote there. So this is not possible. Log base 2 of 0 is not possible. It is undefined.
Our next one is log base 2 of, we're not sure what, equals 3. So I'm going to say my log base is 2, and I'm raising to the third power to find my answer. So 2 to the third power is 8. So I know that log base 2 of 8 equals 3.
Here we have log base 2 of something equals 1/2. So again, rewriting it in our exponential form, we know our base is 2 raised to the 1/2 gives us what on the inside? We've got 2 to the 1/2 is the same as what? So 2 to the 1/2 is the same as the square root of 2. And so I can say that 2 to the 1/2 is the same as square root of 2. That is my answer. Or you could also find the decimal approximation, which is about 1.41.
Our next one says log base 2 of 1/16 equals what? So let's put that into our equation. We know we're log base 2, and then it's raised to some power, and we're going to get 1/16. So I know because it's a fraction, I'm going to have a negative power here. So I want to think 2 raised to what power would give me 16, because then that negative would give me 1/16. So I'm going to say 2 to the 4th power gives me 16. So if that's the case, 2 to the negative 4th power will give me 1/16. So my answer here is -4. So I'd say log base 2 of 1/16 equals -4.
We have one last example here. So we have log base 2 of something equals 0. So if we want to turn this into exponential form, we know our log base is 2. So 2 raised to the 0 power equals what? And you can't use this arrow thing to kind of help you out. 2 raised to what power gives you that inside of our log. So 2 to the 0 gives us the inside. 2 to the 0 power is 1. Anything to the 0 power is 1. So we know that our question mark is 1. So we could rewrite that as log base 2 of 1 equals 0. And that's a true statement. All right, on to the next section here. While the idea behind the ancient puzzle is more than 2,100 years old, the symbol log is more recent. It was created by John Napier, who was a Scottish mathematician in the 1600s. The word log is short for logarithm and represents the power to which a fixed number, called the base, must be raised to produce a desired number. The log function represents the inverse of an exponential function, just as the exponential function represents the inverse of the log function. Use this idea to determine the inverse of each of the following functions, determine the inverses, and write our answers in y equals form. So the goal is to write the inverse of these functions here. Let's kind of go through our arrow diagram example. So let's look at our original function. So if I'm telling the story of x, I see here that x is kind of inside this log base 9. So I have log base 9 of that value. So x is kind of being put inside this log base 9. So if I want to do my inverse, I know that for my inverse, I'm going to start with x, and I'm just going to work my way backwards. To undo a log base 9, we just learned that the inverse of a log function is the exponential function. So if I want to undo log base 9, I'm going to do 9 raised to some exponent. So for my equation for y equals log base 9 of x, I know that my inverse is y equals, we have x, and what is happening with x? X is now going to become the exponent where 9 is the base. So 9 is being raised to the x power. So that would be our inverse function of y equals log base 9 of x.
All right, let's try this with our next equation, y equals 10 to the x power. We're going to talk about our original. In our original, we're going to tell that story of x, which what's happening to x right here, it is the exponent that 10 is getting raised to. So I'm going to say 10 is getting raised by our x. And then if we switch and do the inverse of that, we're going to say x. And if I go backwards, remember our inverse of our exponent is our log. And so we're going to say we need the log base 10 because that's our base of our exponential. So we're taking the log base 10 of our x value. So to write it in our y equals form, we're going to say y equals log base 10 of x.
All right, let's walk through the same process for C and D. Here in C, we have y equals log base 6 of x plus 1. Let's tell the story of x. So we see with our original function, x is being added with 1. Then after it's being added 1, that is all being inside the log base 6. So now we're taking the log base 6 of that thing. So we got log base 6 of all of that. If we want to do the inverse, let's tell the story of x. So again, we're going to undo in backwards order. So we start off with x. The inverse of log base 6 is 6 to some power. The opposite of adding 1 is subtracting 1, and then we're good on that. So let's write our equation. So we have y equals, we start off with x. X now becomes a power with 6 as the base, and then we subtract 1. So our equation would be y equals 6 to the x minus 1.
Our last one that we're going to do is y equals 5 raised to the 2 times x power. So let's write our story of x. In the original, we have x, and first we're timesing by 2. And then that is the power which we raise 5 to. Our inverse, x, we're going to go backwards, and when we have 5 to the power of something, our inverse of that is the log. So we're going to say first we're going to log base 5 of our x, and then the opposite of timesing is dividing by 2. So if we write that in our equation, it'd be y equals log base 5 of x divided by 2.